So next we're going to discuss nuclear half-lives of radioisotopes. So this gives us a little bit of an insight as to how to measure when radioactive decay occurs. So half-lives are the amount of time that it takes a given isotope to decay to 1/2 of its original sample. So for example, if we have carbon-14 and we are monitoring that reaction that goes to nitrogen 14, and here we have beta decay. The half-life here is known to be around 5,730 years. So that means that if you start off with 1 gram of carbon-14, it's going to take one half-life for 5,730 years until 0.5 gram of that carbon-14 remains. And then it takes another half-life for there to be 0.25 grams to remain. So this is not a normal linear relationship that you've seen in many other things. So what we do is we can just multiply the number of half-lives that you've gone through in order to determine how long it's going to take to get there, okay? So the decay curve for these looks much different than it has in other instances. So as you see, I've got that drawn below. If we start with 100% of something, it takes 1 half-life to get to 50%. It takes to the second half-life to get to 25%. It takes a third half-life to get to 12.5%, and it can keep going. So we continue to have like this very slow decay curve for radioisotopes. This is different from other types of reactions. So let's say that you're trying to make this a mathematical relationship. If we start with 5 kilograms of carbon-14, if this question is asking how long it will take to have 0.625 kilograms, there is an equation that goes along with that. But for the purposes of this course, what we're going to do is we're just going to count down how much we start with and figure out how many half-lives that is. So if we start with 5 kilograms, in 1 half-life, we get to 2.5 kilograms. Another half-life, we get to 1.25 kilograms. And another half-life, we get to 0.625. So that means we're going through 1, 2, 3 half-lives. And we can either add those together or just multiply by 3. And this is how many years that is known to be. So there is a difference between fission and fusion. So here's some terms that you should know. Fission is where we have a large atom that is split into 2 or more atoms, and this is what we know as nuclear reactions for the most part on this planet. So we're talking about uranium-235. This can lead to a chain reaction, and that's where you can have things like nuclear energy come about that we know of so far. The other alternative for that is nuclear fusion. And fusions where 2 small nuclei combine and release even more energy. This is something that requires very high heat. This is what powers stars. So the sun runs on this type of energy. There's attempts to make that on Earth, and that is a lot of stuff that's underway still now. So as I've mentioned before, radioactive isotopes are widely used in medicine. As an indication of that, here's a few things. We have what's known as a PET scan. PET scans are positron emission tomography. So we have specific radioisotopes that have short half-lives that are used here, and these can help give a 3D image of organs. You're probably familiar with a CT scan or a CAT scan, and that stands for computed tomography. It's monitored by the computer, and x-rays are targeted at an organ. You can use contrast agents here to get a better view of things, and often those are radioactive. Now, you've probably heard of an MRI as well. This is not radioactive, although there are certain types of contrast agents that can be used here as well. But this stands for magnetic resonance imaging, and the computer monitors energy signatures when it's placed underneath, some body is placed under a strong magnet. And usually this has to do with hydrogen and the uptake of that or H2O specifically in relationship to that magnet. That's a bit more complex, but I won't go into that further. Okay, thank you very much.